Namaskara. We have seen an interesting algorithm for finding the strong connected components of a directed graph. We have seen its working through an example. We have used depth first search twice, once on G, again on G reverse, and then finally obtained the partition corresponding to the strong connected components. Now we need to prove that it indeed works. That is because it is not entirely obvious how, by processing the DFS in a specific order, that too in G reverse, is giving the partition is not clear, right. It is not obvious or direct. So we will take a closer look at the proof. It is a very interesting proof. It is simple and insightful, and one of the most elegant and then wonderful proof. And this shows that the proof of an algorithm as an independent entity has got its own mathematical elegance, beauty, purpose, and so on. Okay. Computation we can do. It is a procedure we can specify, do this computation and that and so on, and then you can give a description of the algorithm. Sometimes from the description of the algorithm its correctness is not clear. In fact, the algorithm is derived based on these type of facts and observations. So if we do this computation, we would get that kind of a confidence the designer gets. So the discovery process is basically you build the mathematical properties and then in line, in conformity with those properties, do some computation so that whatever is guaranteed by those properties is obtained by the algorithm by doing those computations. So they go hand in hand with one another. In certain simple algorithms, the proof will be direct and obvious, but this is a case where it is pretty subtle. Okay. So we will see SCC, strong connected component proof of correctness. So first of all, from the definition we see that the strong connected component of G and strong connected component of G reverse are same. That is because the way in which the strong connected component is defined is, for every pair there must be a path from U to V and V to U. If there is a path from U to V in G, there is a path from V to U in G reverse. If there is a path from V to U in G, there is a path from U to V in G reverse. So the same definition works, and the same connected components you will obtain when you work on G reverse as well. And we have seen that the condensed graph gives an interesting property of these components. Okay. The condensed graph is obtained in the following way: shrink all the vertices in a strong component to a single vertex, and then if there is some edge between some vertex in one component to some vertex in the another component, in the condensed graph draw just an edge. Okay. So this may be a component and this may be a component, this may be Ci, this may be Cj, and there may be edges like this, but when you condense you get Ci and Cj. Notice that the edges can be only in one direction. you cannot have edges in both direction. Okay. That is because if you have edges in both direction, it will create a cycle and connection between all vertices in both directions. Okay. For example, if you can imagine some edge like this, suppose I put that in a dotted one, suppose there is an edge in the opposite direction. Now from any vertex to any vertex you are going to have paths. For example, you want to go from here to here, alright. It is simple. From here you can perhaps come here, take an edge and reach here. From here you can come over here, right. So you see that there is a way to go from one to another. For the opposite direction, you go from here to here, take the opposite one, and from there you can come over here. So between all pairs of vertices, paths exist. Therefore, if there is an edge in the opposite direction, it will merge Ci and Cj into one big super component. If there is any edge from Cj to Ci, it would merge Ci and Cj to a big strong connected component Ci union Cj. That is not the case. A is one component, Cj is another component. Their union is not a component. Therefore, there cannot be any edge in the opposite direction. You can go only from one component to another component one way. There is no cycle. Okay. That is the reason why the condensed graph is a directed acyclic graph. This is the major reason why condensed graph is a directed acyclic graph because of this reason. Okay. Now let us derive one important property of the vertices in a connected component. We have to identify the vertices in a connected component. So let Fc equal to maximum of V dot F, V belong to C. So C is a connected component, it has got vertices, each vertex has got a finish time, maximum finish time among the vertices in a connected component, and discovery time, earliest discovery, and dC equal to minimum of U dot D, U belong to C. Each component has got vertices, each vertex has got a discovery time and finish time. Let Fc is the maximum finish time, the one that has finished in the last, and dC is the earliest discovery time. It is a discovery time of the first vertex in that group of vertices, in that set of vertices. Let Fc and dC be defined in this way. Then we have the following interesting lemma. If Ci and Cj are two strong connected component of G, and if there is an edge from Ci to Cj, that is from some vertex in Ci to some vertex in Cj. That is what we mean by an edge from Ci to Cj. then finish time of Ci is greater than finish time of Cj. So, here is Ci, here is Cj. There is a vertex, there is an edge from Ci to Cj. We will consider two cases, two kinds of edge connections. Okay. Case 1, dCi is less than dCj. That is, the vertex in Ci has got is discovered earlier than the vertices in Cj. The first vertex, let us say u, let u be the vertex with minimum d value, that is, u is the first vertex in Ci that is discovered by the DFS. When you perform the DFS, this component has got several vertices. There is a vertex that has been discovered for the first time. Let u be that vertex. Okay. After entering u, what happens? After entering u, DFS reaches all vertices reachable from u, and they will all be in the subtree rooted at u. All vertices reachable from u are in the subtree rooted at u, because from you entered u and then you visited, then you backtracked, and then you. So, in this way, if a vertex is reachable, that will be in the subtree after it reaches all vert. Thus, all vertices reachable from u are in the subtree rooted at u in the DFS tree. It will be like this. Okay. Notice that C1 is a strong connected component. That means all vertices here are reachable from u. There is an edge from Ci to Cj, some edge. So, through that edge it can reach vertices in Cj. Cj vertices form a strongly connected component. So, any vertex here is reachable from this vertex. Therefore, hence all vertices of Ci union Cj are reachable from u. All vertices of Ci union Cj are reachable from u. They are all here. Therefore, in the subtree Ci union Cj is in the subtree. So, it will visit every vertex, and then when it is finished it will backtrack. Therefore, du when do you exit this and go to its parent? What is the finish time of u? Finish time of u will be much later than finish time of all the vertices in the subtree, because these start and finish earlier and backtrack and so on, and after visiting everything you backtrack from u. Therefore, u dot f is greater than let us say v dot f for all v belong to Ci union Cj. That means u dot f is greater than f of Cj, because Cj is here, all vertices of Cj are here in the subtree and their maximum is this, and this is larger than even that. U dot f is, if the discovery time, if the finish time of u is, u itself is larger, there may be some other vertices with a higher finish time. If that is the case, f of Ci is greater than or equal to u dot f, which is greater than f of Cj, because u belongs to Ci, u belongs to Ci. Therefore, f of Ci is greater than or equal to u dot f, which is greater than f of Cj. That means f of Ci case 2. In this case, we have considered d of I is less than d of Cj, right. Now we are going to assume d of I greater than d of Cj. D of Ci is greater than d of Cj. So, Cj is here, there is some earliest vertex v in Cj, and then you have dCi, there is a vertex u with dCi. D of Ci is greater than d of Cj. In this case, we show that there is an edge here, let us say xy, there is some edge from Ci to Cj. In this case, we note that no vertex of Cj can reach u in Ci. If any vertex can, proof by contradiction, we have seen already. Proof is by contradiction. If there is a way to reach, let us say u, if there is a vertex that can reach u, that path u to x path, y to, so if there is a vertex z, proof is by contradiction. Let z be a vertex which has a path from z to u, then that path plus path from u to x the edge xy and the path from y to z, it will then this union contains a cycle, and that means u is in Cj, right. From every vertex in Cj I can reach u, from u you can reach every vertex because of this cycle. That means u is included in Cj, and this is a contradiction. The reason is Ci intersection Cj equal to empty. You cannot have u in Ci and u in Cj, that is not possible. Therefore, thus no vertex of Cj is connected to u. So, in the reachability of all these things, you will never be there. Therefore, all these things when they are done, they are going to at that time the color of u will be white, it is not even reached. So, you start with V, you explore all the vertices, and in that exploration of the vertices u will be there always, because u is not touched, there is no path. So, no vertex of Cj is connected. This implies DFS starting at V will never reach u, it will never reach u. Therefore, f of therefore V dot f is less than u dot d for all V belong to Cj and u belong to Ci. This implies f of Cj is less than u dot d, f of, but u dot d is less than u dot f, u dot f is less than or equal to f of Ci, that is because u belongs to Ci. So, in both cases we have shown that f of Cj is thus if there exists an edge uv with u in Ci and v in Cj, if there is exist, then f of Ci is greater than f of Cj. Okay, pictorially. There is an edge. Now, we use the contrapositive. If, what is the negation of this? F of Ci less than f of Cj. That is because f of Ci will never be equal to f of Cj, they are indifferent. So, the negation of this is this. If this is the case, if this is the case, then there is no edge from C I to C j. There is no edge from C I to C j. Okay. This is what we are going to use. How we use it? So, start DFS in G power R with the vertex with highest finish time. Let U be such a vertex and C be the strong connected component containing U. Let Cj be any other strong connected component of Gr. Strong connected component of Gr is same as strong connected component of G. So, okay. We start with the highest finish time. Therefore, f of C is greater than f of Cj. Why? This as the highest finish time. So, the finish time of Cj will be smaller than that, since f of there is no edge from Cj to C. Okay. There is no edge from Cj to C in G. Therefore, there is no edge from C to Cj in G reverse. Cj to C no edge means you reversed it. So, from C to Cj there is no edge. Hence, the DFS starting at U will not go outside of C. You are starting with this is C, this is the vertex with 1. There is no edge from C to any other one. If there are any other one, the edges are like this, so they are not useful. So, from U when you start, you cover all the vertices reachable. All vertices reachable will not go. Hence, the DFS starting at U visits all vertices of C and no other vertices of G. It will not go anywhere, it will remain there itself. This implies the spanning tree rooted at U has all vertices of the strong connected component and only these vertices are in the tree. Hence, the forest generated by DFS in GR, hence the forest defines the strong connected component of G. Okay. So, you have a partition of, when you perform DFS you get a forest. So, forest will have several trees, each tree will correspond to a strong connected component, done. Okay. Hence, the forest generated defines it in what way? Each tree of DFS forest would correspond to one strong connected component of G. This is how therefore our algorithm works. The complexity is linear. Okay. Construction of GR complexity. Order n plus m for constructing GR. Again order n plus m for the two DFS we did in the algorithm. That is all. Therefore, total complexity order n plus m. N is the number of vertices and m is the number of edges. So, this completes the discussions on the linear time algorithm for strongly connected components. We have done this on a directed graph. We conclude the discussions on this session at this point. Thank you.